Okay. So first of all, announcements. So the second homework has been posted and I corrected if you have downloaded already, like maybe 2 or 3 days ago, you may download the newer copy. So the only change was about the problem number indexing. So the previous indexing has some issues because I deleted a problem that created a problem, the indexing problem. But now the indices should be okay. So that's the first one. Second, we expect to send you the final project this week. So that's the plan. But I will make an announcement once we do that, and you will receive the data set and instructions for about the final project by email. So everybody will get a slightly different data set, but it will be the same set of open-ended analysis problems. So hopefully we will have a very interesting discussion for the final project in the presentation part of the final project. But I want to say that we hope everybody can use your judgment to do the data analysis. Just be truthful and don't try to guess what's the right answer because, as I said, everybody's data set may be a little different and there may not be a single correct answer is possible. So therefore, we would like to see how everybody approach the problem in a very different way. So that's the final project. Once you receive it, I'll make more explanation of it. So for today, since I'm doing this on Zoom, I'll use the slides to continue our discussion on PCA. So as your final project will involve single cell data analysis, and you may use Seurat, right? Because Seurat is the easy pipeline to use, has been very well implemented with many functions you can do it step by step. So we will follow the Seurat pipeline to introduce the PCA, and then after PCA, which falls into this dimension reduction step, cell clustering. For this step, we have talked about some standard classic methods already, including PCA, including k-means, hierarchical clustering, and model-based clustering, Gaussian mixture model, EM algorithm. We talked about that. But for single cell data specifically, there are some algorithms we also hope to talk about after PCA. So for today, we'll continue talking about the PCA idea and how to determine the number of PCs. So as we're doing this on Zoom, I would encourage you to unmute yourself and speak up if you have any questions, because otherwise, if you type in the chat box, I may not be able to see your message immediately. So on the board on last Wednesday, right, we derived the PCs, like the first PC. Why is it an eigen decomposition problem? But going back to the big picture or background, why do we want to do PCA? The most important question. I think I asked the question to you in the last lecture, and some of you told me dimension reduction. Some of you told me to find the direction that maximizes the variance, right? You tell me these answers. But for single cell data analysis specifically, our hope is to find the important variance and get rid of technical noise, which will also contribute to variance. So not all the variances we see in our data. By variance, we mean that cells are all different. But is this difference biological or is it technical? The answer is that it's both. It's a mix of biological differences among cells and technical differences caused by measurement inaccuracies. So PCA is a step essentially we hope to use to reduce the dimensions of our data so we don't work with thousands of genes, and this dimensionality will make a lot of mathematical operations not ideal. Like Euclidean distance in high dimensional space is known to be not informative. But we hope to preserve the majority of the biological variance. So here, each PC is essentially used to represent a meta feature that combines information across correlated genes. Yeah, so the compression of data into PCs will reduce dimensions. But here the question is, how many PCs should we keep, right? Number of PCs. So we will continue from there. Suppose that I know I didn't completely finish the derivation. We only talk about PC1 as the first eigenvector of the matrix X transpose X, which is a P by P matrix. P is number of genes. For PC2, we hope to continue maximizing the remaining variance, and we want to make PC2 orthogonal to PC1. So that's how we solve for the problem and get the second eigenvector and so on. So that's the math part. But today we're going to talk about the practical selection of PC number. So essentially, what we're plotting here, this is a commonly used PC standard deviation versus number PC plot. So the x-axis is the PC index, PC1, PC2, and what we're showing is the standard deviation of data points in each PC. So basically, when we say PC, we mean that the original n data points, say n cells, are projected into the PC space. So PC1 is essentially an n-dimensional vector, and the values in the vector corresponds to the n cells values in PC1. So one thing I hope to clarify a little bit to our students is the difference between loadings and PCs. So if you recall the notations I used in the last lecture on board, the phi's, the coefficients of the original features are loadings. They are the weights of the original features, while the z's, the projected data, are the PCs. So in other words, PC are data, while the loadings is the map from the original features to PCs. That's the difference. So here we're computing the standard deviation, which is the square root of variance of my n data points in each PC. And as expected, first PC has the largest standard deviation, second PC smaller, so there should be a monotone decrease in standard deviation as we increase the PC number. This is expected. But the question is, where do we stop? Where do we think, oh, in this PC, its standard deviation is small enough, so it's not meaningful. I don't need to include this PC and anything after it. What's your intuition? Any ideas from our students? If I want you to pick one PC number to stop, where would you pick? Yeah.
Kevin?
Yeah, please go ahead. Just unmute yourself.
Kevin.
I would choose the one where there's like a marked difference right afterwards.
Yeah.
So maybe PC8.
PC8, this one. This is what you will pick.
Yeah.
Okay, will you include it or exclude it?
I would include PC8 because I feel
Okay.
like the delta between 7 and 8, the standard deviation is quite large.
Okay. All right. How about Melanie? I think she also tried to say something.
Oh, I meant the same point.
Okay. All right. Thank you. Okay, so that's what your intuition told you. And this is similar to the choosing K problem for our K-means clustering. I want to look for an elbow. And I mentioned this technique and over here, but we didn't formally introduce it. I said to choose the elbow, there are several algorithms you may use. One algorithm is called a needle algorithm. So it was introduced in this Towards Data Science blog. If you're interested, I'll post the slides after the lecture. And it was from this computer science conference paper. But it's very widely used because it's very simple and easy to implement. So what it does actually is that if you have such a curve, right? So in our case, it goes downward, but this is upward. So you can just add a negative sign to your data points so we can make our curve to be like upward. So that's easy. So what you do is that you first draw a straight line to connect the two endpoints. And from each point in the curve, on the curve, you find the perpendicular distance from the point to the straight line. Okay, you do that. And then what would you do? So you see here the dash bars in the caption. The dash bars are rotated 45 degrees. And I think I should say more specifically, this straight line corresponds to y equals x. So it's a 45-degree line because the axis is normalized. So x-axis and y-axis both go from 0 to 1, normalized axis. And you had the straight line, and then, of course, these segments perpendicular to this 45-degree line would also be 135 degrees, right, from the x-axis. And then what you do is that you rotate each bar 45 degrees. Okay, so basically that's the B. Shows the same data, but this time the dash bars are rotated 45 degrees. The magnitude of these bars correspond to different values used in needle. So what it means is that once you rotate these bars 45 degrees, you will get a curve in C. Okay, so you will see this one. So essentially, it's nothing special, but just this curve, you rotate it to be horizontal because it used to be 45 degrees. And then what you will do is that you look at this curve and you pick the point where it's maximized. So basically, it's this value. So the value whose x-axis is this one, like this one. So basically 0.2 something. And that's how you find the knee. That's it. So I would say intuitively, you're just looking at the value whose perpendicular distance to the diagonal line is maximized. That's this algorithm. So depending on whether it's upward, you call it knee, or downward, you call it elbow. That's just subjective. Any questions about this? No. Okay. Yeah, it's an intuitive algorithm. So you choose K, and that's PCA. So a good thing about PCA, I should add few more thing is that you can run the whole PCA because you're doing eigenvalue decomposition for your X transpose X, P by P matrix. And then you can choose wherever to stop. You can stop at 7 PCs, 8 PCs, or 9 PCs, but that won't change your PCs. So for example, if you choose 8 PCs, then the first 7 PCs among your 8 PCs will be the same as if you choose 7 PCs. So the cutoff doesn't affect what the PCs are like. Okay, so that's PCA. Now I'm going to talk about this method, which was introduced for single cell data, but it is actually more general than that. It's called GLM PCA, Generalized Linear Model PCA. So single cell data is a good example to apply this method, but the method itself is just, how to say, similar to the difference between generalized linear model and linear model. So in single cell data analysis, the default in SURAT is that the data you input into PCA are not the original count data. They are actually the normalized data. We told you this before, log 1p CP10K. That means you first normalize your cells, each cells to have total equal to 10K. That's called CP10K values. And then you plus 1 to add 1 to each CP10K value, and then you take log. The plus 1 is to avoid log 0. And 0, after you add 1 to it and then take log, it will stay at 0. That's the reason. So people observe that empirically, such data are like Gaussian, more like bell-shaped, if you look at each gene's value in different cells. So then they input such data into PCA and do PCA. But this paper, which questioned this approach, said that the current normalization procedure, such as log of counts per million, so it's about log 1p CPM million, and feature selection by highly variable genes, we also talk about that, produce false variability in dimension reduction. So we'll see what they mean by false variability. And then they propose simple multinomial methods, including generalized principal component analysis for non-normal distributions, like the original count data. You can model that, you can do PCA on count data directly, and feature selection using deviance. So it's basically trying to modify Gaussian data like PCA into count data like GLM PCA. So it's a generalization. So first, let's look at the author's motivation, which is you will have data distortion by doing this log 1p CPM. So this is the UMI count of one gene in cells. So we're plotting a histogram of the distribution. It should look like a unimodal distribution, right? There's only a single mode, single peak here. But if you do CPM, you see something happens. That is, zero count stay as zeros, but the non-zero counts, because of the scaling to make every cell's total as CP as a million, you actually drift these non-zero counts away from the zero count. So you created a gap here. And then you further apply log2 transformation to CPM plus 1. You create a bigger gap. So that will make the data look bimodal. You have a zero proportion here and you have a non-zero proportion here. So this is what the authors called distortion. So they are against this transformation because they think that it distorted the data. Okay, so then what's their way of doing the PCA? So let's first look at their review of PCA. So it's another way to look at a PCA, different from what we talk about, because in the last lecture, what I talked about is the maximization of variance perspective. We want the data projected to the first PCE to maximize the variance. That's our perspective. But they're looking at the second perspective, and it turned out to be equivalent because of Gaussian data-like properties. So the variance is a square form, and also this minimize mean square error perspective is also in a square form. So this perspective says, oh, for PCA, we want to look at a low rank representation of our data. And hopefully from the low rank representation, we can have a good reconstruction of the original data. So what does this mean exactly? Yij is the raw count. Zij is the normalized and transformed version of Yij, such as log CPM. The PC objective function is we want to have mu I and mu j to represent factors or to represent factors. Both are L-dimensional. So essentially, so Yij, if I use our notation, is gene j in cell I. So I want to represent my cell I instead of using the original gene number as a vector. So because, for example, in the original space, each cell I can be 1,000 dimensional because I have thousand number of genes. Here, I just want to represent the cell I in a low dimensional way, say only L dimensions, maybe 50. And also, I want to represent my gene J. Instead of using all cells, I want to use just L dimensions. So UI and VJ are both L dimensional. And you can just do this mu I inner product VJ to get a scalar. And this scalar is what I represented using only L dimensions instead of the original dimension space, was the EIJ, right? So I'm trying to use this low dimension to approximate the original data. And what is the benefit of doing that? The benefit is that if your cell I is represented by L dimensions, and these L dimensions are essentially the LPCs. So I'm just getting cell I's embedding in each of the L dimensions, call that mu I. And VJ is what? VJ is the original gene J's contribution to the LPCs, like the L loadings. Each the gene J will have a loading in each of the LPCs. So basically, we call mu I as cell I's PC scores, Vj as gene J's loadings. So their inner product is what we call the reconstruction of the original data based on PCs. So that's another advantage of PCA. That is not just finding a low dimension embeddings, but you can also use the low dimension embeddings to reconstruct the original data. And of course, you will lose something, but you hope that the difference is only due to noise, not due to signals. Okay, so let's just read what the author wrote here. The UI are called factors or principal components, and VJ are called loadings. The number of latent dimensions L controls the complexity of the model. Minimizing of the MLE is equivalent to minimizing the Euclidean distance metric between the embedding and the data. It is also equivalent to maximizing the likelihood of a Gaussian model. I want to add one more thing. It is also equivalent to maximizing the variance in the first PC, variance and following variance in the second PC, and so on. So these are all equivalent, and I think that is the mathematical elegance of PCA. So what the author's arguing here is that this loss function, to minimize the square loss, is equivalent to maximizing the likelihood of a Gaussian distribution where the mean is just the inner product. And this is a well-known fact, just as in linear regression, the least square solution is equivalent to the maximum likelihood estimator of Gaussian distribution. What is ZIJ? ZIJ, we said here, is the normalized value, log transform value of gene J in cell I. It's one of the entries in the single cell count data. Okay, so any questions regarding this alternative formulation of PCA? All right, if not, then let's continue. So as I mentioned, right, there is a connection with linear model. Let me first talk about linear model. So linear model, or we can start from the simple linear regression. Yi is the response of our ith data point. Xi is the predictor, a single predictor, scalar value predictor of the ith data point, epsilon I, random error. Some typical assumptions is that the random errors of different data points are independent, and the random errors follow a Gaussian distribution with a common variance. So this is called normality and homoscedasticity assumptions. So if we have more than, and if we want to use a matrix form, I just say it. For the matrix form, what we can do is that we stack the intercept and this predictor, single predictor, into one so-called design matrix. So the benefit of doing that is that we can also stack the intercept and the coefficient into a vector. So then the matrix right multiplies the vector will give us exactly what we have over here for each row. Okay, so the first row multiplied by beta is essentially beta 0 plus beta 1 x1. Okay, so we can have this matrix form for the simple linear regression. Y equals x beta plus epsilon. So we are basically stacking the n data points by row. And we also can refer to the ith row of the design matrix as xi transpose. Okay, so I'll just quickly say that for the linear model, it used to introduce the generalized linear model. Once you understand this generalization, we can go back to the Gaussian PCA and generalize it to GLM PCA. So that's the logic. And so now if we consider more than one features or predictors, so previously we just have one feature. Now, if we have P minus 1 features, we can have the design matrix as P columns because we still need to keep the first column to be ones to represent the intercept. Okay, then in this linear model, we can rewrite it in two layers. The first layer is what we call the systematic structure, fixed relationship, no randomness, which is about linking mu I, which is defined as expectation of yi. So this triangle is a mathematical symbol for definition. It's defined as, and it's assumed to be just x transpose beta, which is the same as here. X transpose ith row of x multiply beta. So this is a vector multiplication, inner product. So we get a scalar. And this just means that each yi's expectation or mean is a linear combination of our features. And the features coefficients is a common beta. Beta doesn't depend on data point I. Beta is common. Okay, that's how we explain the expectation for each response. The random structure is about how we can explain why the data don't perfectly fall in a line. So yi may look roughly like on a line, but not perfect. And that is what we attribute to randomness. And we're thinking about the random errors. Here, epsilon 1 to epsilon n are following a Gaussian distribution. And here we're using a matrix form. So epsilon is an n-dimensional vector. This is an n-dimensional Gaussian distribution. 0 is an n-dimensional zero vector. And sigma square is this common sigma squared, but we're multiplying it by an m-dimensional identity matrix. So just a matrix form Gaussian distribution, but all the epsilon 1 to epsilon n's are independent. So if we put it together, then essentially we can write that yi is just normal distribution. It should be a scalar, and this is a typo. Let me just quickly cross it out. So this shouldn't be there. So it should be just yi follows xi transpose beta, a scalar, and the variance is sigma squared. Okay, so essentially, this is the random structure telling us the relationship between yi and mu I. Mu I is explained by our features using a fixed relationship, but yi is not equal to mu I due to the randomness explained by Gaussian distribution. All right, so any questions regarding this part of the review for linear regression? So the key thing here is to understand that the random structure is Gaussian. Okay, I'll just pause here for maybe for 5 minutes and see if we have a question or a hand up. Okay, if no question, let's continue. GLM. Why do we want to generalize? So the first motivation is that the response yi does not seem to be a Gaussian random variable. So this is a common example in a lot of our social science data. That is, the response of an individual may be binary. For example, if it's a voting data, there are only 2 votes, then it's 0 or 1. But still, we want to see how each individual's predictors or covariates or features can influence the voting decision. And the predictors can include age, education, and salary. The predictors can be numerical or categorical. So what do we do? Then you can see this assumption here. It's obvious that we cannot assume yi to be Gaussian, right? Because Gaussian data cannot be binary. Then what do we do? So we follow the logic to break down the logistic regression into random and systematic components. So here for yi being binary 0, 1, the only reasonable distribution is Bernoulli, right? Only Bernoulli can be used to describe a binary random variable. And Bernoulli has only one parameter, the probability of getting 1. So for yi, we refer to its Bernoulli probability as pi I. And we expect that the predictors, such as age, education, and salary, would affect this person I's pi I. Okay, how do we link expectation of yi, which is pi I, to predictors? So here, again, to summarize, the random structure describes the discrepancy between the observed response yi and the expectation pi I. And we know for Bernoulli random variable, there is a property about its expectation, pi I, its variance is pi I times 1 minus pi I. So in other words, given a person's age, education, salary, we assume that this person has a probability pi I of voting a 1. But we consider that this person's actual voting outcome to depend on its Bernoulli distribution. So it's not absolute, especially when pi I is 0.5. That is the most uncertain case because that's when variance of yi is maximized. So pi I times 1 minus pi I is maximized at pi I being 0.5 because that's the most uncertain case. So we need to account for this uncertainty here. And that makes sense intuitively, right? Because this person is unsure whether to vote 0 or 1. If pi I is 1, then this person will only vote 1. If pi is 0, then this person will only vote 0. Okay, so recall that for the linear regressions systematic structure, which is what we use here, mu I equals xi transpose beta, we can continue using it. We can assume that pi I, the mean of yi, is just a linear function of the features. But it doesn't make much sense since on the left-hand side, pi I must be between 0 and 1. The range is known for Bernoulli probability. While the right-hand side, the range can go from negative infinity to positive infinity because your values here for like salary, age, they're not constrained, right? They're not constrained to the 0 to 1 range. And you also didn't put any constraint on your beta. So the two sides don't have ranges matched. So what do we do? So there is a sequence of thoughts to help us match the two sides. The first thought is to convert pi I to something we call the odds ratio. The odds ratio is the probability of getting 1 over the probability of getting 0. So if we have pi I divided by 1 minus pi I, then the range will go from 0 to positive infinity. So basically, when pi I is 0, it's 0. When pi is 1, you have 1 over 0. That's positive infinity. So on the left-hand side, you are closer. You have 0 to infinity. The right-hand side can be negative. Negative infinity to positive infinity. Still don't match. How about we further modify it? That is, we give this odds ratio a log surrounding it. Because, you know, log can only take positive input, but it will get a negative output if the input is less than 1. So in other words, you can see log of 0 is negative infinity. Log of 1 is 0. So by adding this log, you are expanding the left-hand side to the whole range. Negative infinity to positive infinity. And this log odds ratio has a name as a logit function of pi I. So now you can assume this left-hand side to be equal to right-hand side because they're matched. But again, this is your assumed systematic structure. That is, how would your predictor or feature effect influence my yi, the probability of getting a 1? Okay, and in the GLM, generalized linear model, specifically in our case, logistic regression, where yi is binary, we call this transformed mean on the left-hand side eta I, and eta I is by default defined as xi transpose beta. We call that linear predictor. So the question is, how do we link this linear predictor to our parameter of interest, which is pi I? Pi I here is our mean of yi. How do we link them? And this logit function is the link. So that's why we call it a link function. So in my other class I'm teaching right now in this quarter called Stats 205, we have extensive discussion on this logistic regression model and generalized linear model. Okay, but for this class, since our focus is not on this model per se, I'll just be brief here and give a high level overview. And any questions from our students? I'm curious how many of you have seen this before, like the logistic regression. I think many of you should have, right? Because it's a popular method. Yeah.
So this is in replacement of PCA, right?
Yeah, so we haven't talked about PCA yet. We're trying to first talk about generalizing linear model to generalized linear model. So from linear model to GLM is the first step. If we understand this, then we generalize PCA to generalized PCA to GLM PCA. That's the logic. Does that make sense? All right. If there are no more questions, let's continue. Okay, let's look at this logic function of pi I. What does it look like mathematically? So you can see that it transforms your probability pi I from the range of 0 to 1 to negative infinity and to positive infinity. So that's what the function looks like. So it's a monotone transformation. Smaller pi I will give you smaller larger pi I. Okay, now let's talk about Poisson regression, another example of GLM. So here the yi's are counts, non-negative integers. So this is very like our single cell data. The pi i's take values 0, 1, 2, and so on. So the simplest count distribution is Poisson. Poisson has only one parameter, mu I. Mu I, again, is the mean of yi, expectation of yi. And mu I must be non-negative. So this is the probability mass function of yi for Poisson distribution. And yi's mean, expectation, and variance are both mu I. So then here the question is, how do we link this mu I to the linear predictor eta I? Eta I is defined as xi transpose beta. So it's just a short notation for x transpose beta. How do we link them? So here we also have a difference in range. So mu I has range 0 to infinity, while the right-hand side has the whole real line, negative infinity to positive infinity. So based on the logic we just gave you, it just makes sense to take a log of mu I to make it real valued. And that's what we did. So here the link function is log function. All right. Then here the interpretation of the effect of our feature j, like beta j is the coefficient of feature j, which means its effect. So its effect is actually on the log of our response expectation. It's not on mu I directly, it's on log mu I. Okay, so that's GLM. From LM to GLM, what we changed is the random structure. So it's no longer Gaussian. It is Bernoulli or Poisson or something else. Second, we changed the relationship between mu I and eta I. In linear model, mu I is just equal to eta I. So the link function is identity function. Logistic regression, logit mu I. So in that case, we wrote pi I, but pi is basically mu I. Logit mu I is eta I. In Poisson regression, log mu I is eta I. Okay, now going back to the PCA. So I'll just skip a few slides to go back to here. This is the alternative formulation of PCA, okay? Zij, the data before PCA, is assumed to follow a normal distribution whose mean is a low-rank inner product, okay, of cell I's PCs times gene J's loadings. Their inner product is the mean of the normal distribution, okay? And we say that minimizing the difference between Zij and the inner product squared, minimizing this is equivalent to maximizing the likelihood of the normal distribution. So now we want to generalize the idea. Here, Zij is assumed to be normal, but the authors argue that they don't like this transformation. They want to use counts directly. So in this case, they don't want to use the transform Zij, but the original Yij. But Yij are counts, right? What might be reasonable? So looking at the previous example where normal becomes Poisson, here it makes sense to think How about Yij follows a Poisson distribution? But in the Poisson, the mean is an inner product of two low-rank vectors. So that's the idea here. This is exactly what the authors wrote in their paper. So they replaced the Gaussian model with a Poisson model, and then they model the UMI counts directly as Yij times Ni. Okay, so they're just trying to make some cell library size Ni, the total counts here as the cell library size, and multiply by a low rank thing. But here the thing is that they cannot directly use the inner product since they don't want to put any range constraints on UI, the PC scores of cell I, or VJ, the loadings of gene J. So they want the values here to be real value. So therefore, their inner product could be negative, could be positive, could be any real value. But that doesn't satisfy Poisson's requirement that the mean must be positive or non-negative. So therefore, they apply the exponential transformation to convert a real value to a non-negative value. Okay, or alternatively, as we mentioned in a previous lecture, if you don't like the constraint placed by Poisson that its mean is equal to its variance, we can change Poisson to negative binomial by introducing another parameter for gene J. We call that phi J. So this can allow for so-called over-dispersion. That is, the variance can be bigger than the mean, and this may agree better with many count data. Okay, so this is their model. And then essentially, what they're doing is to maximize the likelihood with either Poisson or negative binomial, and by maximizing the likelihood, they want to find the corresponding UI and VJ. In particular, they want to find the corresponding loadings of the genes. If you find them, then you can solve for the UI correspondingly. And that's it. So they're using MLE to do this GLM PCA. And that's the high level idea. And I have to say that the first mention of this idea was in this 2002 paper. It was the old version of the NeRPS conference, the machine learning conference. And later, yeah, the authors here applied them to the single cell data as a very useful application. Any questions? So I'm skipping the details of doing the MLE, maximum likelihood estimation, but that's an optimization problem, trying to find UI and VJ. And the motivation is that the data they want to find low dimension embeddings for are non-Gaussian. Let me see. Okay. As an illustration, consider the GML PCA with Poisson approximation to a multinomial likelihood. So I skipped the multinomial part, just say Poisson. The objective function to be minimized is simply the overall deviance. Okay, I'll just quickly introduce this jargon. I mentioned that in my other class, but deviance is basically negative log likelihood. That's what it's basically about. So in this case, minimizing deviance is equal to maximizing the likelihood. So here the author tried to expand the log mu ij to be written as a sum of the UIL VJL sum. So what I'm going to say here is, let me see how I can do the annotation. Okay, what I try to say here is, if you can see me. So this thing is basically an expansion of this. It's just expanding the inner product. So they're just writing it out. So you know that in the optimization, they're going to find mu I, UI as L values and VJ as L values. That's it. And the size factor is the total number of UMIs in cell I. Okay, so I will say that GLMPC is an optimization problem. And they still will get an output UI and VJ. So every cell I will now be represented by L elements as its LPCs. You still get the PCs for cells. And for every gene J, you will get L loadings, meaning how much does gene J contribute to each PC. So the end result is interpreted in the same way as PCA, but you are using a different modeling assumption and you don't need to transform your data to become more like Gaussian. That's the advantage. But the disadvantage I can also say is that this optimization is much slower than just the PCA. Because PCA is basically just eigenvalue decomposition of X transpose X. So there's a price to pay. And I think that is also part of the reason why GLM PCA, after this paper was published, hasn't been widely used or that widely used like 6 years ago, 5 years ago, compared to the Seurat PCA, even though this issue was pointed out. Yeah, I think the computational time is definitely a reason, but I also know that another group of authors recently proposed a faster version of GLM PCA. Yeah, computationally much faster. We'll see. Yeah, I'll see whether people want to pay the additional computational time as a price to gain the better properties of the method. So that's what I want to say for GLM PCA. Any questions? So the generalization, the G part, is very, very similar to the idea of going from LM, linear model, to GLM.
Since we have a model now, can we use this to find like confidence intervals for the PCs, or is that really not like of interest?
Good question. Yes, we can. Yeah, definitely. That is something definitely we can. But that's a good question. There's also another way to interpret the PCA in the Bayesian way. So in the Bayesian way, that means that you can add priors for your U elements and V elements because you have a lot of them, right? And you know that that's a general principle in parameter estimation. That is, the more parameters you estimate, given the same number of data points, the more uncertain your each estimate will become. So therefore, the Bayesian idea is that by tying up these many parameters into a prior distribution, it's like a constraint. Okay, they should be distributed in that way. Maybe a Gaussian distribution as a prior. That means that you are trying to tie these values to a center of that Gaussian prior, but you allow for some dispersion around the center. So if you do it that way, you are essentially stabilize your parameter estimates using your prior assumption, then you will be less uncertain. But the prior is something you introduce. Yeah, so that's another level of subjectivity. Yeah, that's a very good point. So if you want to make some interpretation of how certain you are for your loadings, right? And also for your PCs. Okay. Another thing I want to talk about is very related to PCA, but it's for a different, purpose. So this is I would say it's not so well known nowadays, but I think it's a very, very useful technique to know. It's called MDS, standing for multi-dimensional scaling. So the idea is you don't have original data. You don't have your X matrix. That is, for your N data points, you don't have its original feature values. But what you get is a distance matrix, N by N distance matrix, where you know the distance between each pair of data points or observations. And what you want to see is that you want to project your data points into a space, maybe two-dimensional, so you can see the data points. And you hope that by projecting the pairwise Euclidean distances in your 2D space is close enough to the input distances. So you're converting input pairwise distances into a two-dimensional data matrix. That's the purpose. So it is a visualization method to help people visualize data. Because otherwise, just looking at the N by N distances may be too abstract. Okay, so that's the thing. And of course, we will use 2 dimensions for most cases because our eyes are very used to 2D plots, right? And it's very easy to do that on computer, even though we can do 3D, but 3D plots are not easily visible than compared to 2D. You need some transparency and some 3D structure there. Okay, so what does MDS do? So our hope is to preserve pairwise distances, and we hope to find data points y1 to ym to represent the original n data points. And our input is the D matrix n by m. And please note that the D values, Dij, means the distance or dissimilarity between data points I and j is not necessarily a metric. So metric is a mathematical concept that requires certain things, like you require the metric to be non-negative, to be symmetric, and to follow the triangle inequality. So these are the things. But this dissimilarity may not satisfy the triangle inequality. So that's not in the requirement in our computation. Okay, so what we hope is to output y1 to ym. So I just set it to 2 dimensions for simplicity, in the hope that the Euclidean 2-dimensional distances between y and yj, so we use this L2 norm to mean Euclidean distance is similar, close to Dij, the input. So this is just a very quick recap of what we mean by L2 norm. So we just sum of the square distances of the 2 data points in every dimension. Sum over dimensions, take the square root of the sum. Then we can also rewrite it in a vector form. So we can write this distance as yi inner product with itself, yj inner product with itself, so both are scalars, minus 2 times yi inner product of yj. But this is the square of the Euclidean distance. Essentially, I can get rid of the square root, and then for the sum, I just make it into a vector form. That's it. So squared Euclidean distance can take this inner product itself plus inner product itself minus 2 times the cross inner product.
Wait, I'm sorry, can I ask a question?
Yeah.
How do you get from my math knowledge is lacking? How does yi transform yi equal what you have under this radical?
So
Do those equal?
so you're talking about how do we go from the first equation to the second equation?
Yeah.
Okay, so because we're not doing the derivation on the board today, I can quickly say that get rid of the square root because we're taking a square here, and you open up the square. Then you will have summation of yik square. K goes from 1 to p. You will have that. And that sum of yik square across k is essentially yi transpose yi.
I see. Okay, thanks.
Yeah. All right. So then our question is, okay, so this is called gram matrix B. B is defined as what? It's defined as y times y transpose. So I'll quickly say that here y is stacking the yi's by row. So it's an m by 2 matrix, so P equals 2, 2-dimensional. So y is just a data matrix. And y times y transpose is an m by n matrix. So B is an m by n matrix. And here, Bij is just yi transpose times yj. The reason we are interested in this matrix is because it contains everything we need in this second equation, right? Yi transpose yi is just bii, this is bjj, and this is bij, right? So if we have that, then it's easy to continue from there. Okay. Let's see. Okay, so we want to use this gram matrix, and then I said this already. So then this Euclidean distance between y and yj square is just expressed in terms of bii, bjj, and bij. We hope this to be close to dij, the input Euclidean distance, or dij squared. Okay, so for now, let's simply say that we set an equation, okay? We set an equation dij squared, this is the input, equals bii plus bjj minus bij, which is this square of Euclidean distance 2D in the 2D space of our yij. So our hope is that first we find this B matrix, and then we decompose this B matrix into Y times Y transpose. So we find Y. That's the hope. And we want to be exact here, so we just set equation. And also we want to avoid some challenge regarding identifiability. Because here, as you can imagine, we are just inputting pairwise distances. But the n data points we are looking for, y1 to yn, can be anywhere, right? We can shift them in the 2D space. So they're not identifiable. We cannot fix them in a fixed locations. So to address the identifiability, we basically assume that in each of the 2 dimensions, the n data points are centered at 0 with mean 0. So we are basically fixing them instead of allowing them to shift freely. Okay, solving this problem. Okay, now it's a set of algebra. To basically, we're trying to solve a system equation. It's the equation system. So essentially, first thing we consider is the constraint, right? Since we have the constraint that the sum of the yi's in each dimension k equals 1 or 2, is zero. So we can first find that by taking the sum of bij. Bij, by definition, is yi transpose yj. If we take the sum over I, then you can see that we open up the inner product as yik times yjk, k goes from 1 to p is 2. Then we can basically have the double sum, 1 over I, 1 over k. And first, do the sum for I first, but put k outside. And then we have sum of yik from I from 1 to n, fixing k. And this is 0 by our constraint. So therefore, we have sum of bij, I goes from 1 to n being 0. Same argument, we can have sum of j going from 1 to n being 0. So we can have that being 0 first, taking the sum of bij for I or j. Okay, then if you take the sum of dij squared, then you see you will have, and taking the sum for I, okay? And then sum of bii, and since bjj doesn't involve I, it's just itself multiplied for n times bjj. And the cross term has a sum 0. And this first term is essentially the trace of the B matrix. We're taking the sum of its diagonal elements plus mbjj. Similarly, we take the sum of dij squared for j. We can get n times bii plus trace b. Finally, we take the double sum of dij squared for both I and j. So then you can see that we take the sum here for I, we get another trace. We take the sum here for j, another trace. So it's 2 times n times trace of e. We have this set of these 4 equations. Okay, and with these 4 equations, you can actually solve for bij because you want to just solve for bij based on the dij squared because this d is your input matrix. That's just the reason. So essentially, we just need to take the following sums: dij squared, sum for I, sum for j, and double sum. But of course, we need to do some normalization to divide by the number of entries in the sum. So essentially, bij will be, the result is that dij squared minus this d dot j squared minus this d dot di dot squared minus d dot dot squared. And the total, the difference, times minus 1 over 2. So you solve for bij. You are halfway there because once you get every bij, you get a B matrix. And once you have that, you finally eigen decomposition. You do eigen decomposition to get the y. Essentially, if you can do the eigen decomposition for B as this, right? So basically, eigenvector multiplied by the eigenvalues multiplied by the transpose eigenvectors. So essentially, you take the square root of each of the eigenvalue, then you get a square diagonal matrix, because this is a diagonal eigenvalue matrix, multiply that to the eigenvector, and that's how you get a y. So essentially, you see the similar thing to PCA, because PCA also involves eigen decomposition. So what is the equivalence between the two things? Oh, one more thing I want to say is that because here we only want to keep 2 dimensions, what you can do is that you just keep the top 2 eigenvalues and you take the square root of them and you keep the top 2 eigenvectors. That's how you get the top 2, the 2-dimensional representation of data or embeddings that can most preserve the pairwise distances. This is multidimensional scaling. So I want to say that the equivalence between MDS and PCA is if you have the input here, distance matrix D, calculated based on the original input data, high-dimensional data for PCA. Suppose that you use the high-dimensional data to define Euclidean distances of your data points, call that as your D. You input that into MDS and you keep the top 2 dimensions. Essentially, that will be equivalent to your 2-dimensional PCA. So that's where they're equivalent. But the thing is that for MDS, you don't need to give the original data. You can just input the distance. And sometimes for some data, you don't have the original data available, or your distance may not be calculated as a Euclidean distance. So that makes MDS more flexible. So it's a more general thing, while PCA requires the original data to start with. Yeah, so that's what I want to say for this part. Any questions? So if you think this linear algebra calculation here may be too overwhelming for you for now, that's okay. I hope you to understand that. I hope that you can understand that MDS is basically finding the 2-dimensional embeddings y1 to yn whose pairwise Euclidean distances in the 2D space are very close to the original input data matrix, original input distance matrix.
So
Okay.
will the MDS output be identical to the top 2 PCs?
Yes, that's
Oh,
right. Yeah, if the input matrix is Euclidean distances of the high-dimensional space. Yeah, this is something you can try. Just play with it to see whether that's the case. But of course, I think here you can also consider some of the, let me see. Yeah, I think so. Yeah, you should get an identical result. Okay, so any more questions? We still have some time left for this lecture. So for this stack of slides, I can continue to talk about, to move forward a little bit to talk about the clustering. But I want to make sure that we are on the same page. So we talk about dimension reduction. For single cell data, Seurat default is still doing data transformation followed by PCA. But the GLM PC was proposed to saying that log1 PCPM distort the data. So you want to work with count data directly. Okay. All right, so then let's look at our next lecture. Yeah, maybe I should continue talking about dimension reduction since we're already here. And let's look at this. So we'll talk about a few more dimension reduction techniques, including NMF, non-negative matrix factorization, PNMF, projective non-negative matrix factorization, and ICA, independent component analysis, which are related but sometimes easily confusing concepts. Okay, so These are also commonly used methods, but for slightly different purposes compared to PCA. So first of all, non-negative matrix factorization. It is a very popular technique, first introduced in 1994, but popularized by this Nature article in 1999. Since then, the number of publications reference the technique has grown rapidly. So in the Nature paper, it is using it for showing that the low-dimensional features can represent some components in facial images. So that's why it was made popular. So it's very similar to PCA. It also tried to decompose a matrix, N by P matrix. Okay, here I'll just follow the notation here. A P by N matrix. So it's just that here the rows and columns are transposed. Instead of having the rows as data points, columns as features. In this set of notation, the rows are features or dimensions, columns are data points, okay? And this input matrix is non-negative. So all the values are non-negative. We're still doing this linear decomposition, trying to find a low-dimensional representation of the n data points, which is now h. So h is n data points in a lower dimension, maybe k or r dimensional space, okay? And this W P by R is what we call the loading matrix for PCA. How each of the P features are represented in the one of the new R dimensions. Okay, yeah, just pay attention to this swap of the features and the data points. So the constraint here is that the elements in W and H must all be non-negative. Okay, so I already said that. Analogous to PCA, what is the loading matrix? What is the score matrix? W is the loading matrix, how the original features are assembled into new features. H is the score matrix, how the n data points are represented in the new R dimensions. Yeah, I already said that, right? So we have R meta features. Okay, and this is a cartoon showing NMF. So all three matrices must have non-negative entries. So again, this product of the two matrices can let you reconstruct the original matrix. So that is first row of W times first column of H gave me the first entry in the X matrix. And we hope that this reconstructed value we call X tilde is close to what's in X. Okay, but this non-negativity has one big advantage, which is what? Sparsity. Sparsity means that you have a lot of zeros. The reason is that you must have a lot of zeros in both W and H so that you can make their product close to X. Otherwise, you will, because you see, without negative values, you don't have cancellation. You cannot have a negative value to cancel out a positive value to make the sum small. Here you have only 0 and positive values. So everything just add up. There's no cancellation. So if you want to get a small value in the original matrix, then you cannot have too many positive values in W and H because otherwise the product will be large. So this is a very, very important property of forcing things to be non-negative. That is, you can force to have sparsity. And what is the advantage of having sparse W and H? So here is the loading matrix. If you see that I have many zeros in this first row, what does that mean? Because here, first row is R dimensional. It means the original feature one's loadings in the new R features. So having a sparse row means that the original feature one only participate in certain new features. Or if we look at column-wise, for the first new feature, how many contributions do my original P features make? So these are the values in column 1. If I have many zeros in column 1, it means that only a small number of original features contribute to my first new feature. And that will make the new feature more easily interpretable. While versus PCA, in the loading of new feature one, PC1, if we have many positives and negatives, they have cancellation effect. But it will be hard to just argue, say, which features make contribution, because every feature may have some non-zero coefficient loadings to this new feature. So that will make interpretation less straightforward. Does that make sense?
So can I just restate can I basically because it's non-negative, if there's a value, then that loading matters. But in PCA, because you can't have both negative and non-negative, it's harder to
Interpret, yeah.
But
So
what if you took the absolute values of the loadings in PCA? Would that be equivalent to the non-negative major factorization?
no, I don't think there's one-to-one correspondence between the two. So basically, PCA allows a feature to have a negative contribution to the new feature, right? New meta feature. But NMF only allows positive contribution. That is the major difference. So which means that for NMF users, you only think positive contributions are interpretable or is what you care about. You don't want to interpret negative contribution. So you are putting yourself in a more constrained space for doing this decomposition. So therefore, you made a very good point. That is, when we choose the method, which method to use, it should be based on our application and our data, how we understand our data. So for example, in this Nature papers figure, right? So this is your original data point, which is data point I is a facial image. So the pixels are the features. So you see that you have eyes, you have mouth, but what you can do is that if you do the NMF, all right, and then NMF give you how many? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 49 meta features. So these meta features are going to be used to replace the original pixels. So you do dimension reduction. But you can see that this new image is projection to the 49 meta features is as this. So you will just store your image not in the original format, but in this format. This is the projected data, much smaller, easier to store. But each of the 49 meta features, if you look at their correspondence to the original features, you can see some features correspond to the eyebrows, some features correspond to the mouth. So they are very interpretable because they correspond to parts of the original images. So in this case, you only want to keep positive loadings because that's what you can interpret. Otherwise, if you make it positive or negative, then each meta features loadings will be very messy to look at. You cannot tell what they mean. Does that make sense?
Yeah.
Yeah, so here the major goal is not the reconstruction. I can tell you that if you keep the same number of load dimensions, PCA will give you a much better reconstruction. And there's a mathematical theorem to say that PCA will give you the best linear load dimension data for reconstruction. But here, that's not your major purpose. Here, you want to keep some interpretability. So here, having the loadings sparse and non-negative will make interpretation easier.
So if you gave this problem to PCA, what would the ending matrix look like? Not the far right example, right?
So I think in the Nature paper has a one, let me see. The Nature paper has one for PCA result. It should look more messier. Yeah. Yeah, but actually we're running out of time. Let me see whether I can find that image quickly to give you the idea. Yeah, okay. I think this is a good figure to take a look. Let me change my screen sharing to this one. Can you look at my browser?
Yeah.
This is the thing. So if you look at this figure, principal, yeah. This figure is what you're asking for. Same image, you do PCA versus NMF. PC is the top. So every meta feature, you see, the first PC preserves most of the information in the face, but the later PCs become something like this. So not as straightforward as like decomposition as
So
NMF.
it's completely different.
Yeah, yeah,
Yeah.
yeah.
Okay.
Okay, all
Can
right.
I
Yeah.
ask you about homework questions, or are you busy right now?
Okay, so maybe we can end the class here and I can stay here I can stay in the Zoom for a few more minutes to answer your questions. And I'll stop the recording here.
Yeah.